Welcome back, everyone, to MAE170. This is lecture 12 in week number 8. So today we're going to talk about frequency response methods, and in particular, we're going to develop a way of drawing Bode plots. I'm sure you're already familiar with Bode plots. You've probably used them, but perhaps you don't know why we use them or what they actually represent. So we're going to do that in detail today. So everything starts from focusing on the steady state response. So remember, the response of a system can be divided into two parts. The first part is a transient, and then we have the steady state part. Technically, steady state refers to the time that goes to infinity. However, for practical purposes, we refer to the steady state response as the response that happens after time when the time is greater than the settling time Ts. Now, the key difference from what we've seen so far is that we're going to focus on inputs that are sinusoidal. So far, we've seen the response to inputs, to impulsive inputs, step inputs, or ramp or acceleration inputs. However, now we're just going to focus on the reaction or the response of systems when the input is a sine wave. Throughout the course of this lecture and the following, we're going to assume that the system is stable. Because, of course, if the system is not stable, the response will simply go to infinity. All right. So as usual, we consider our system. Now we don't really care whether the system is open loop or closed loop. That's going to be something that we're going to see later. So we simply have our system in this box and characterized by the transfer function g of s. The input is our usual r of s and the output y of s. Okay. So as I said, the input is going to be a sine wave. So in the time domain, and I'm going to do this in the time domain because when we plot functions, it makes more sense to visualize things in the time domain. So r of t is a sine wave. So we have the amplitude of such sine wave is a0, and the frequency, so on and so forth, and the frequency is omega. So a0 is the amplitude, and then the period is given by 2 pi over omega, where omega is the frequency of the sine wave. Okay, so if we have an input that looks like this, the output can be of three kinds. And once again here, I'm considering the output for t that is sufficiently large, or for t that is greater than the settling time. So just before describing the output, you should already think, and please, I'm going to ask this question and you try to answer. I won't give the exact answer to the question, but because I want you to try and think about it. Does the final value theorem apply when the input is sinusoidal? So does the output have a final value? Yes or no? Think about it. Okay, so the three cases for in terms of output are the following. So we can have a function that always in the time domain looks like another sinusoidal with another amplitude, AF, and then we have sine of omega t plus v. So in this case, well, I should, sorry, let me draw it. All right, so the output has a different amplitude, so AF. And the frequency is the same, so the period is still 2 pi over omega. The only thing that changes is that the output function is shifted by a quantity phi. So there's a phase, either lead or lag, depending if phi is positive or negative. And once again, this, let's consider this as t equals t of s. So the shape of the output is after that. Now, the second option is that the output might look like this. So here we have a superposition of different sinusoidal waves. One that is the same as case A, so with the same frequency as the input. And then we have the sum of a bunch of other sinusoidal waves that are associated with purely imaginary couples of poles of the transfer function of the system. So each pair of purely imaginary poles of G of S will dictate one of these waves that are summed up together, and the overall result might look like this purple curve here. Might look, it might be also different. And once again, this is settling time, so whatever you see is meant to be after the settling time. Now we can also have another type of input, type of output, and that is when both the input and the transfer function describing the system share same poles. So when that happens, and you already know this, but unfortunately, the output just blows to infinity. It still keeps the same frequency, but it oscillates and linearly goes to infinity. So we can have these three scenarios. Just a simple wave with the same frequency as the input, then a combination of multiple sine waves, and one of them has the same frequency as the input. And in case C, we have a wave that blows up and so diverges to infinity. Therefore, in this case, the system is unstable. And if you don't remember that, I'll refer you to the lecture when we talked about stability. Okay, so here I wrote down a summary of what it just described. Case A, we have the output is a sinusoidal with the same frequency as the input. But generally with a different amplitude and different phase. And this happens when the poles of G of S have all negative real parts, or at most one pole at the origin. Case B, instead, when we have a superposition of sinusoidals, the output, the signal, in terms of time, is composed by one sinusoidal as in part A, so with the same frequency as the input, but different amplitude and phase. And then the other sinusoidals have frequency equal to the n, where n is just a number, of natural frequencies associated with the imaginary poles of g of s. For instance, if the poles of g of s, they can be on the, could be on the imaginary axis like so. So in this case, we have n is equal to 3. So of course, in this case, g of s is marginally stable. So the important thing is that the frequencies associated with the pairs of imaginary poles of g of s, they must not be equal to the input frequency. Because if that happens, then we go to case number C, where the response, there's just a resonance, and the response just goes to infinity. So we really don't want that from happening. So if g of s is marginally stable with n greater or equal to 1 couples of purely imaginary poles with natural frequency omega and I, so with I that goes from 1 all the way to n, and then we have the frequency of the input wave that equates one of the natural frequencies characterizing the system, then unfortunately the input just goes to infinity. All right, so now let's take a look at a numerical example to see how we can obtain the output based on a sinusoidal input. So in this case, let's consider an input that is equal to sine of 1/2 t. So this sine wave has amplitude equals to 1, and the frequency is equal to 1/2 radians per second. And then we're going to construct our system so that it does the following. And now we're going to do this, although it really looks like a block diagram in the S domain, but it's really just a logic diagram that can be applied in the time domain. So we have the input. We split the input into two. Then one part we're going to multiply by 2. And then this is going to be summed up with the other branch. And instead, the other branch, what happens is that we're going to integrate the input from 0 to t in dt. And then we're going to sum up whatever the result is from that branch. And the result of the summation is our output. So if you wish, whatever it's inside here kind of describes g of t, or the system. So you see here, it's not really in the S domain, but we can do the same thing in the S domain, and we shall, in fact. But remaining in the time domain, because that's what we've seen, we can construct directly the output as 2 times the input plus the integral of the input itself. So what do we have here? We have 2 times sine of 1/2 t plus the integral from 0 to t of sine of 1/2 t dt. So this is equal to 2 sine of 1/2 t, and now the integral of sine of t is minus 2 cosine of 1/2 t, and then this has to be evaluated at 0 and t. So this is equal to 2 sine of 1/2 t minus 2 cosine 1/2 t plus just a constant 2. All right, so now let's focus on the two sinusoidal terms in this output, that is 2 sine 1/2 t minus 2 cosine of 1/2 t. And here we're going to use a trick. So when we have a times sine of x plus b cosine of x, that can be transformed into square root of a squared plus b squared times sine of x plus phi, where phi is the arctangent of b over a. So in our case, we have that a is equal to 2, a is the coefficient in front of the sine wave, and b is equal to minus 2. So square root of a squared plus b squared is equal to square root of 4 plus 4, which is square root of 8. And then the phase, phi, is equal to arctangent of minus 2 over 2. So this is equal to minus pi over 4 in radians, or if you wish, that is also equal to minus 45 degrees. All right, so we have now the actual output in the time domain that is equal to square root of a times sine of 1/2 t minus pi over 4 plus 2. So you see that, well, for now, let's forget about this constant that we're adding. We're just, the constant can be there because we're just simply shifting the output upwards or downwards with respect to the x-axis, so the time axis. So it doesn't really matter much. We should really focus on the sinusoidal part of the response. So as you see, the response has the same frequency of the input. The input was simply sine of 1/2 t. So the output has the same frequency, but now has a different amplitude. In fact, it is magnified by a factor of square root of 8, which is about 2.23. So it's a little bit more than twice in terms of amplitude, and it lags of 45 by 45 degrees. Okay, so here we started with a function in the time domain. We ended up with a function in the time domain without even invoking a Laplace transform, and so we're very happy. Unfortunately, though, as you know very well, every time we're dealing with control systems, we always have the transfer functions in the Laplace domain. And well, I said unfortunately, but that's actually a fortune because that simplifies calculations a lot. So let's take a look at this very example, but now in the S domain. So remember that R of t was sine of 1/2 t. So the Laplace transform of this sinusoidal wave is equal to 1/2 times 1 over s squared plus 1/4. And that is because, generally speaking, if we have a function r of t that is equal to sine of at, its Laplace transform, so r of s, is equal to a over s squared plus a squared. So now a in this case is 1/2, so we're going to have 1/2 over s squared plus 1/4. What about g of s? Well, g of s is simply 2 plus the integral, and everything multiplies the input. So 2 is just a factor, and then the integral in the s domain is 1 over s. So if we want to obtain the usual just one fraction, then we can rewrite this as 2s plus 1 over s, or 2 times s plus 1/2 over s. So g of s is stable. It actually has a pole in the origin, but this falls into the category A. If we go back, I wrote that if the poles of g of s have all negative real part, or at most have one pole at the origin, such as in this case, then the response is simply a sinusoidal wave with the same frequency as the input. That checks, we already know the answer to that, but with, of course, different amplitude and phase. So the fact that we have the pole at the origin will be the cause of the constant of +2. But nevertheless, the shape of the output is always the same. It doesn't matter if it is translated or not. Okay, so in the time domain, if we want to find the output, that is equal to the transfer function times the input. So we have 2 over s times s plus 1/2, g of s, and our input, r of s, excuse me, is 1/2 times 1 over s squared plus 1/4. And this you can by doing a partial fraction, the composition, and then taking the inverse Laplace transform, that gives you exactly the result that we found earlier. So 2 plus 2 sine of 1/2 t minus 2 cosine of 1/2 t. And well, I invite you to do the missing steps. And so once again, using the same rule that we saw earlier, y of t is 2 plus square root of 8 times sine of 1/2 t minus pi over 4. So this checks, and so you see, of course, things are the same whether we do the calculations in the time domain or in the s domain. We must find the same answer. Okay, so here just a little note that the only operations that you can actually do when dealing with linear time invariant systems are summation and subtraction, multiplication by scalar, integration, and differentiation. In order to build the output starting from the input, in this example that we've just seen, we used a multiplication by scalar and the integration and then a summation. Okay, so generally speaking, what we find is that starting with an input of amplitude A0 and frequency omega, the output is a function with a different amplitude, which we're going to call AF as in final, and the same frequency, but shifted by a phase angle phi. And of course, we can have also a constant, just in case we have a pole at the origin. Here, H stands for Heaviside function, which is another name to call the step function. So far we've always called it step function, but in the time domain that can also that is known as Heaviside function. All right, so now let's take a look at the amplitude ratio between the output and the input. So in other words, let's take a look at the ratio between AF and A0. And we're going to always refer to the example that we've seen. So the final amplitude was square root of 8, whereas the initial amplitude of the signal was simply 1. So the ratio is square root of 8 itself. Now, from now on, we're going to use the decibels to measure the amplitude ratio between the output and the input. And then the way, mathematically speaking, that you find the decibels is to take 20 times natural logarithm of whatever you want to transform. So in this case, is the ratio. So A final divided by A initial. So in terms of decibels, the amplitude is 20 logarithm of square root of 8, which is about 9.003 decibels. What about the phase difference? Well, the initial phase was 0, and the final phase was minus 45 degrees. So the phase difference is just minus 45 degrees. So the output lags by 45 degrees with respect to the input. Okay, great. But remember, this is valid for a frequency of the input equals to 0.5 radians per second. So what happens if we change the input frequency? Well, normally we would get a different amplitude ratio between the two signals and also a different phase difference. So what we could do is, by taking a different value of the input frequency, we would have to compute the amplitude ratio and the phase difference. And so let's actually do that. But first, let's report the values for the frequency that we've used. So in this case, we have on the x-axis the frequency, omega, but the scale is logarithmic. So we have 0 0.01, 0 0.1, 1, and 10. And the interval between 1 and 10 is called a decade. And that is the same as the interval between 0 0.01 and 0 0.1, for instance, is still a decade. And same thing between 0 0.1 and 1. So a decade is the interval between two frequencies whose ratio is 10. So starting from 0 0.01, if we multiply by 10, we get 0 0.1. So we say that we are one decade above. And then if we take 2 decades, we get at 1, and 3 decades, we are at 10. So it's 3 decades is really multiplying your value by 1,000, 10 to the power of 3. So the decade is, if you can think about it as the exponent of 10. Okay, so 0.5 in the logarithmic scale is not really halfway between 0.1 and 1. It's more towards 1. So this is our 0.5. So let's say that 903 is here. So we have our point here. And we can do the same thing for the phase difference. At 0.5, we said that we have a phase difference of minus 45 degrees. Now, in order to find other points, we need to vary the frequency of the input function. And so if we did that, we could construct a whole curve which will kind of look like this. For the amplitude ratio, and for the phase will look like this. So here, minus 45. It's when the frequency was 0.5. All right, so you see that here we have the same problem that we had when we wanted to compute the closed loop poles of a transfer function when varying the value of the parameter k. So we would have to change the parameter k, compute the closed loop poles, plot them in the complex plane, then change the value of k and recompute the closed loop poles, and so on and so forth. So instead of doing that directly, we found a way to see the whole range of possibilities. In other words, to plot the root locus. In this case, we're going to do the same for these two plots. So we're going to find a way to draw all the possible ratios between the final and initial amplitudes of the signals and the phase difference as the frequency varies. So we don't have to plot point by point, but we can develop a set of rules so we can draw the actual whole curve. And these two plots are known as the Bode plots. So the Bode plots are nothing but two plots that indicate the ratio in terms of decibels, so 20 logarithm of the ratio of the amplitudes of the output divided by the input and of the phase difference. So how do we do that? Well, I just said something that should have sparked something in your mind. I said 20 logarithm of the ratio of the amplitude of the output divided by the input. Does that sound familiar? Output divided by the input. Isn't that the transfer function of the system? Yes, it is. So we can come up with the Bode plots for a certain control system by just studying its transfer function. All right, that's what we're going to do. And how is that associated? So how is the transfer function associated with the Bode plots? Well, we can find the amplitude ratio by looking at the magnitude of the transfer function, and the phase change can be retrieved by looking at the phase of the transfer function. Now, the only difference now is that the transfer function has to be evaluated at s equal I omega. So usually s is a complex number, sigma plus I omega. And if you also remember the contribution of the real part in terms of time is e to the minus sigma t, whereas the contribution of I omega, it is a sinusoidal. But we also know that since the system is stable, as per the assumption that we made earlier, as time goes by, e to the power of minus sigma t will go to 0 because sigma is positive. Or, sigma, let me repeat this. The contribution associated with the real part is e to the power of sigma t. So if sigma is negative, such as in the poles for a stable system, that e to the power of sigma t goes to 0 for time that is high enough. And once again, here we're considering things when time is after the settling time, so the contribution of the real part doesn't really matter. So we're left with the contribution of the imaginary part, which is the sinusoidal part. Therefore, we're going to substitute into the transfer function I omega whenever we see the Laplace variable s. So in other words, what we're doing is we're substituting the complex frequency with the real frequency, omega. So let's see what this looks like for the example that we've seen. G of s was 2 times s plus 1/2 over s. Now we're going to perform the substitution, so we simply have s equals I omega. And so now we have g as a function of I omega. So it is 2 times I omega plus 1/2 over I omega. Okay, so as I promised, and we will see in this example, the 20 logarithm of the ratio between the final amplitude and the initial amplitude is simply equal to 20 logarithm of the magnitude of the transfer function. So this is a more general case. We don't really have to specify omega. Just remember that a frequency is always positive. So omega is greater than 0. So in this case, we have 20 logarithm of, and now we need the magnitude of the numerator. Well, first we have the magnitude of the coefficients, which remain 2. Now we have the magnitude of the numerator, which is square root of, imagine a real part squared, so 1/4, plus imaginary part squared, so omega squared, over the magnitude of the denominator, which is simply omega. All right, so using here properties of the logarithm, we can rewrite this as 20 logarithm of 2 plus 20 logarithm of 1/4 plus omega squared, everything to the power of 1/2, minus, because this is at the denominator, 20 logarithm of omega, and that is also equal to, so the first term remains the same. Now the second term, the exponent of the argument of the logarithm can be taken in front of the logarithm, multiplying the coefficient of it. So we have 20 times 1/2, therefore 10 logarithm of 1/4 plus omega squared minus 20 logarithm of omega. So this is the general function that if you plot this function, you will get the dashed plot that we saw here in the first of the two body plots. However, if we want to retrieve the exact value of the ratio in decibels for omega equals 1/2, all we have to do is just to insert 1/2 into this function, and let's check that we indeed are finding the same value. So logarithm of 20 logarithm of the magnitude of g evaluated at I 1/2 is equal to 20 logarithm of 2 plus 10 logarithm of 1/4 plus 1/2 squared, so another fourth, minus 20 logarithm of 1/2. So the second and third, no, sorry, my bad. This becomes 20 logarithm of 2 plus 10 logarithm of 1/2 minus 20 logarithm of 1/2. So that is really 20 logarithm of 2 minus 10 logarithm of 1/2, which is also equal to 20 logarithm of 2. And this is just to review some logarithmic properties. This is minus 10 times logarithm of 2 to the power of -1. And once again, we can take the exponent and multiply the coefficient outside the logarithm or in front of the logarithm. So we have 20 logarithm of 2 plus 10 logarithm of 2. So this is 30 logarithm of 2, which is 9.03 decibels. And we found exactly the same thing. So once again, only simply taking the magnitude of our transfer function, we find a general expression. And if we plot such expression, we can find the entire body plot for the magnitude ratio. When it comes to the phase difference, as I said, now we have to look at the phase of the transfer function. So the phase of G evaluated at I omega. So let's write G I omega once again. That was 2 times I omega plus 1/2 over I omega. So what is the phase associated with such transfer function? Well, we have the phase associated with 2, that is arctangent of imaginary part over real part. So this is simply 0. Plus arctangent. So now we have this term over here. Imaginary part is omega divided by the real part, which is 1/2. And then we have minus. Now we're focusing on the term at the denominator. Arctangent of imaginary part is omega divided by 0. Now omega is a positive number. Therefore, arctangent of something positive divided by 0 tends to 90 degrees. So overall, the phase difference is given by, or the phase here, it's really the phase of the output is given by arctangent of 2 omega minus 90 degrees. For omega equals 1/2, then we have that the phase difference between the output and the input is given by arctangent of 2 times 1/2 minus 90. So we have arctangent of 1, which is 45, minus 90, and then we have the minus 45 degrees, which we've seen earlier. So everything checks. All right, very good. So now it doesn't really matter what the output is. We can extract all the information that we want, regardless of the input, regardless of the input, just by looking at the transfer function. So normally the transfer function of the system, what we do is we factorize it in terms of its zeros and poles. So what's written here, it's simply that. You might not recognize it, but let's see this in detail. So we have K, which is just the constant gain. Sorry. Constant gain K. Then we have all factors that are associated with real zeros. And then we have complex conjugate zeros. And each pair of complex conjugate zeros is associated with its natural frequency omega n L and damping ratio zeta L. And of course, at the denominator, we can have real poles and complex conjugate poles as well. Furthermore, we can have also poles at the origin. Here I just wrote down as if G of S at just poles at the origin with multiplicity capital N, but of course, we can also have zeros at the origin. So the only difference now is that instead of writing the factors as, for example, if we had a real zero, so if G of S had only a real zero, normally we would write it as S plus 3. Now instead, we want to write it as 1 plus S times a constant tau. So we have to gather 3 and write it as 1 plus 1/3 S. So in this case, we have that K is equal 3, and then we have tau that is equal to 1/3. So all these taus and omega n, whether they refer to zeros or poles, they're called breaking frequencies. Not break in, but breaking frequencies or cutoff frequencies or I think there's another name for them. Well, I don't recall it now, but they're usually named breaking frequencies or cutoff frequencies. All right, so this is sort of the canonical way, canonical form to write down the transfer function when we want to analyze it and come up eventually with Bode plots. Now, the reason why we factorize it in all this term is that since the systems are linear, then each of these factors is going to have a contribution, is going to have their own small Bode plots, and then we can sum up, we can superimpose the small Bode plots associated with all these factors that I just circled with different colors and come up with the overall Bode plot associated with the transfer function G of S. So we had the constant gain K, then the poles are zeros at the origin, of course, at S, then the real poles or zeros in the canonical form are 1 plus S tau. And when it comes to pairs of complex conjugate poles or zeros, well, they're associated with 1 plus 2 zeta S over omega n plus S squared over omega n squared. And of course, remember that the last step is to substitute S with I omega. Oh, here it is, what I was talking about. So tau to the minus 1 and omega n are known as the breaking or critical. Oh, that's the, the term that I had forgotten. So breaking or critical or cutoff frequencies. So if I'm asking you what is the critical frequency associated with this real pole, then you have to write down the pole, the factor, in terms of 1 plus s tau, and tau has the same units of time, so tau to the minus 1 has the same units of frequency. Okay, so as said, we're going to see all the contributions of the single factors, and then we can come up with an overall body plot, but just superimpose the contributions of the factors. So let's start with the simplest of them all, which is the constant gain. So now let's consider a transfer function that is simply a constant. So g of I omega is k. So if we want to compute the magnitude of such transfer function, the magnitude is simply 20 logarithm of absolute value of k. What about the phase? Well, that the phase is arctangent of imaginary part, so 0 over k. So depending on the sign of k, the phase can either be 0 if k is positive, or 180 if k is negative. So if we wanted to draw the body plots for a constant gain, let's start with the magnitude plot. Well, that is simply a constant equals to 20 logarithm of absolute value of k. So that is just constant line. And here the vertical axis intersects the horizontal axis not at 0, because technically omega is 0 when we go all the way to infinity towards the left. So you can draw the vertical line at any intersection that you want. Obviously, what you can do is just focus on a range of frequencies of interest. And normally that range of frequencies comprises all your cutoff frequencies, or critical frequencies. Okay, so when it comes instead to the phase plot, we said that the phase can either be 0 for positive k, or 180 for a negative k. So if we had an input, let's say sine of omega t, and your transfer function was -1, well, the amplitude of your output wouldn't change, it would still be 1. So the actual logarithm of the ratio would be 0. But the output would be in opposition of phase, because it would have a difference of 180 degrees. And that's because we have -1, k is negative. So that was the simplest of the body plots, when the transfer function is just a gain, or at least when we analyze the constant contribution, the constant part of the transfer function. So now let's take a look at the contribution of poles and zeros at the origin. I'm going to work on the left of the screen, and I'm going to consider the case of the pole, then everything that you see on the right is the contribution of the zeros. And I'm not going to repeat the analysis for the zeros, just know that it is exactly the same, but it's flipped with respect to the x-axis. We're going to see what I mean. So in this case, we have that if we have one pole at the origin, we would have 1 over s, right? And if s is equal to I omega, then g of I omega is 1 over I omega. What is the magnitude of such transfer function? That is 20 logarithm of absolute value of 1 over I omega, which is simply 20 logarithm of 1 over omega, or 20 logarithm of omega to the power of minus 1, which is minus 20 logarithm of omega. So you see that the magnitude in the logarithmic scale is a linear function with a slope that is negative. So the slope is minus 20 decibels per decade. If we let's say consider a frequency of 10 radians per second, then the magnitude ratio is minus 20 times logarithm of 10, which is 1, so minus 20. And if we increase by 1 decade, so we get to a frequency of 100, so logarithm of 100 is 2, and minus 20 times 2 is minus 40. So we went from minus 20 to minus 40. So in 1 decade, we decreased of 20 decibels, and that is linear in the logarithmic scale. What about the phase? Well, the phase is the angle of 1 over I omega. So that is minus, because that's at the denominator, arctangent of omega over 0. And so this is simply minus 90, and that is constant throughout all the spectrum of frequencies. Now here what I've added is that if we have multiple poles at the origin, so if we have n poles at the origin, then the magnitude is going to just be multiplied by the number of poles. So we're going to have minus 20 times n logarithm of omega. So we're going to just change the slope of the constant line. And in terms of the phase, we're going to have minus 90 times the multiplicity n. But now let's focus on just one pole at the origin, so n equals 1. And if we want to draw the magnitude plot, then as predicted, this is just a constant line that passes through 0 when omega is equal to 1, and the slope of such line is minus 20 decibels per decade. So if at 1 we are at 0, it means that at 10 we are at minus 20 decibels, and so on and so forth. You see that on the other, on the right-hand side of the page, we have instead the contribution magnitude-wise of a 0 at the origin, and as you see, everything is flipped. So the only difference is that now we have a constant line that increases by 20 decibels per decade. Okay, so in terms of phase, we have a constant contribution of minus 90. And of course, for the 0, we're going to have plus 90. Let's move on to considering real poles or zeros. So poles and zeros that are not at the origin. So in this case, just by considering one real pole, we have that the transfer function is 1 over 1 plus I omega tau. And again, the only thing that I've done is substitute I omega or S with I omega. Okay, so we're going to do exactly the same thing. So I'm going to go a little bit faster. Now we take the magnitude of this. So it's 20 logarithm of 1 over square root of 1 plus omega squared tau squared, which is also equal to minus 10 logarithm of 1 plus omega squared tau squared. So this magnitude, so this function for the magnitude is not linear, is not constant, but really depends on the frequency. So let's take a look at what happens at the extreme. So for omega that tends to 0, then 20 logarithm of the magnitude tends to 0 because it tends to actually minus 10 logarithm of 1. Logarithm of 1 is 0, therefore it starts at 0 for very low frequencies. Then when the frequency matches exactly the critical frequency of this real pole, then in other words, by substituting omega with 1 over tau, we have that our function becomes minus 10 logarithm of 1 plus 1. So we have minus 10 logarithm of 2, which is about minus 3 decibels. So at the cutoff frequency corresponding to a real pole, the magnitude is minus 3 decibels. What happens finally when omega is much greater than the cutoff frequency? Or in other words, when omega tau is much greater than 1, then 20 logarithm of the magnitude of the transfer function becomes minus 10 logarithm of omega squared. Or, and this is again an approximation, or minus 20 logarithm of omega. So you see that this is what we've already found for the contribution in terms of the pole at the origin. So for frequencies that are much higher than the cutoff frequency, the Bode plot of the magnitude behaves like the one for the pole at the origin. When it comes to the phase, well, then this is simply arctangent, minus arctangent of the real, the imaginary part. So it's tau omega divided by the real part, which is simply 1. So that's it. And once again, let's see what happens when the frequency tends to 0, then the phase tends to 0 as well. For omega that it is equal to the cutoff frequency, then we have minus arctangent of 1, therefore minus 45 degrees. And for the frequency that is much higher or tends to infinity, or it's much greater than tau to the minus 1, we have that omega tends to minus 90 degrees. So let's draw the Bode plot associated with this real pole. So the way of doing this is you can do it in two parts. First, we can draw the asymptotic plot, and that is done as follows. So you have to draw the cutoff frequency, 1 over tau, and you find it and you mark it on the plot. Then you come from very low frequencies and you stay at 0 until you hit the cutoff frequency, and then you start with the constant line whose slope is minus 20 decibels per decade. So this is the asymptotic plot. And of course, if you had a real pole with multiplicity 2, then difference would be that the slope would be multiplied by the multiplicity, so minus 40 decibels per decade, for instance. Now, if you want to get the actual plot, then what we know is that at the cutoff frequency, the value is indeed minus 3 decibels. So you can draw the actual plot, sort of asymptotically converges to 0. If you go for low frequencies, then it passes through minus 3 and then asymptotically reaches the constant line at minus 20 decibels per decade. And of course, if you take a look at the contribution of the real 0, we have exactly the same thing, but it's just flipped with respect to the x-axis. Now, something similar can be done with the phase. So what you want to do now is always you want to mark the cutoff frequency, but now you have to do one extra thing when you're drawing the body plot in terms of phase. You take 1 decade before, so you take your cutoff frequency and divide it by 10, and then mark that value, and then mark the value 1 decade after, so at 10 times your cutoff frequency. You know that at your cutoff frequency, the value of the phase is minus 45 degrees. So once again, what you can do is to first draw the asymptotic plot, which is 0 for very low frequencies. Then at 1 decade before your cutoff frequency, you start drawing a line with constant slope that intersects minus 45 at your cutoff frequency. You continue until you hit 1 decade after, and so at this point you'll be at minus 90, and then you continue straight. So this is sort of your asymptotic plot. If you want to draw your actual plot in terms of frequency, then you have to smooth it out, and it's gonna look like something like this. So you have to make sure that at your cutoff frequency, it is exactly minus 45. Once again, if you had a multiplicity 2, for instance, that at the cutoff frequency, you would have minus 90, and the asymptotes will settle at minus 180. Similarly, when it comes to the real 0, everything is flipped. You go from 0 to plus 90. Okay, so now the final part is just the contribution of the complex conjugate poles and zeros. So let's rewrite the transfer function. So here in this transfer function, we have nothing at the numerator. We have the denominator, which is a second order polynomial in omega. And this is because we've substituted s equal to I omega. Now here I'm gonna just show you the case for complex conjugate poles. Then once again, for the zeros, you have just to flip with respect to the x-axis. So wherever we're subtracting phase, you have to add the same amount of phase. And instead of decreasing the amplitude, you will increase. It's just a specular symmetric. So the only thing that I'm going to do here is rewrite this transfer function so that at the denominator I have clearly, I can write first the real part and then the imaginary part. And that is because when you take the square of I omega, that becomes minus I omega squared. And so that is actually a real part. So when we take the magnitude, so 20 logarithm of the magnitude of the transfer function, that is 20 logarithm of 1 over square root of, now we have real part plus imaginary part squared. So this becomes minus 10 natural logarithm of whatever we have as argument of the square root. Now, the only thing that is different when we have complex conjugate zeros, instead of having the minus in front of 10, we're going to have a plus. Okay. Notice also that here the function will be not only a function of the input frequency omega, but will depend also on the damping ratio. So we're going to have different curves for different values of the damping ratio zeta. All right, so once again, let's take a look at what happens for the extreme cases. If omega goes to 0, then the magnitude goes to 0. For omega equals to the natural frequency, we have that the magnitude is minus 20 logarithm of 2 zeta, or plus 20 logarithm of 2 zeta for complex conjugate zeros. And for frequencies that are much higher than the natural frequency associated with a pair of complex conjugate poles, we have that the magnitude is equal to approximately minus 10 logarithm of omega to the power of 4, which is minus 40 logarithm of omega. So once again, a linear function in the logarithmic scale with the slope of minus 40 decibels per decade. Of course, plus 40 in the case of complex conjugate zeros. All right, finally, the phase, well, that is arc minus arctangent of 2 zeta omega over omega n over the real part, which was 1 minus omega over omega n squared. And once again, we would have a plus for the 0. Let's consider the 3 extreme cases when omega is very small, tends to 0, then the phase tends to 0 as well. For omega that tends to, or that is equal to the natural frequency, we have that the phase is minus 90 or plus 90 for the case of zeros, and at very big values of the frequency, then the phase is minus 180. So once again, what we can do is to first draw an asymptotic plot for the magnitude and the phase, and then adjust it for the actual plot. So in terms of magnitude, we're going to do something similar to what we saw for real poles. We start at 0 and we draw all the way till the cutoff frequency, and then now we go down with a constant line, but the difference is that the slope is now minus 40 decibels per decade. And what about the actual plot? Well, the actual plot are going to be a bunch of curves that depend on the value of the damping ratio. So we can have something like this. So let me change the color. And then as the damping ratio increases, we're going to have some peaks. And you can see a better plot than what I'm drawing in your book. That's actually figure 8.10 at page 531. All right. So actually, this is the opposite of what I was talking about. This is the direction of increase in terms of the damping ratio. So for damping ratio equal to 0, so for undamped system, if we excite the system with the same magnitude corresponding to the natural frequency of one pair of the complex conjugate poles, then the amplitude will go to infinity. But as we damp a little bit, there's a little bit of damping, the peak will shift to the left, and that peak occurs at the value omega r, which is omega n times square root of 1 minus 2 zeta squared, and that is called the resonant frequency. The value of the peak is, your book calls it mp omega, 1 over 2 zeta times square root of 1 minus zeta squared. But this happens only when the damping ratio is less than square root of 2 over 2, because for higher values of the damping ratio, so for these lower curves, they don't have a local maximum. Their overall maximum is 0. So remember, if you're asked for the peak value at resonance, well, that happens only when the damping ratio is less than about 0.7. Okay, so last thing, let's take a look at the Bode plot for the phase. Let's start with the asymptotic plot. So here it's going to be a little bit different. It's just going to look like a step. We go all the way to the omega n, and then we go down at omega n. Our phase is minus 90 precisely, and then we decrease until we hit minus 180. And here we're going to draw a bunch of curves because it depends always on the value of the damping ratio. But all these curves pass through minus 90. So the extreme case of omega equals 0, then we would follow the asymptotic plot. So as zeta increases, we go this direction. And you can draw the effect on the phase. They're relevant, once again, between one decade before and one decade after the cutoff frequency omega n. Of course, when we're talking about complex conjugate zeros, everything is flipped. The magnitude will just has to be flipped. Instead of having a peak, we're going to have a dip, but whose value is the same, but with the minus sign. And the phase is going to be increased instead of decreased by the same value. Okay, then we're going to take a look at some examples of the body plots, but the concept is that once you have a transfer function, you find all its factors in terms of real poles, real zeros, poles at the origin, constant, complex conjugate zeros and poles. You draw the contribution of each of these elementary components, and then you can superimpose their effect for both the magnitude and the phase and come up with the overall body plots for the transfer function. Okay, so this is all for today, and I'll see you next time. Take care.